I was told by the organizers that we have people in the audience with very different backgrounds. So I will not talk as much about the beamline itself. I will talk mostly about the technique. I will give a short introduction into technique. And for those who are more interested in real application, I invite you to practical session where I will show more real example and real way how it works in case of our beamline. So we are going to discuss now X-ray powder diffraction, and I will start from the very beginning. What is diffraction by itself? So we assume by diffraction the bending of waves around different corners of different obstacles, apertures, or whatever. So instead of propagating straight forward, the wave can turn. And we are looking at the way how it turns. When we have just one obstacle, it is maybe not so interesting. The things become much more interesting if we have a serial of obstacles. Like, for example, we can take a very simple C wave and look how it passes around the wave breaker. So we can see it very nicely from satellite image, that the plane wave that comes to the shore, it passes through these holes and it starts to turn. So it goes around the corner like this. What is most interesting for us is that if we have a series of apertures, the neighboring waves start to interact. We call this interference of the wave, and this is where all the techniques comes from. So in this zones, you can immediately see that we have a very complex pattern of interacting waves. And if we put the screen not like the shore over here, which is very close, but if we increase a little bit the distance, we will see the picture more or less like this. So after passing the holes, the waves start to propagate in well-defined directions. If we increase a number of holes, so here it's modeled by just 2 holes, but if we put more, we will see only very narrow directions where the wave really propagates. And in all other directions, we will have essentially 0 intensity. This is the effect on which all the diffraction techniques is based on. The interesting thing is that we can reconstruct. So by analyzing the directions where the wave go, we can reconstruct the pattern of these apertures through which it passed. So this is what happens at one-dimensional case, such as C wave. If we, instead of just a line, we imagine a grid, so 2-dimensional grid of some obstacles, we will see, of course, also 2-dimensional diffraction picture, and this is also widely used just in simple nightclubs. So this is what you can easily buy for your nightclub. So you put the laser here, you create a grid, and you see this pattern of diffracted beams. It can be very different depending on the grid. And on the other way, so if you want to have some pattern, you can construct the grid that corresponds to it. This is how it works in more usual cases. How the crystals? The crystal is essentially a 3-dimensional grid, so it is periodic in 3 perpendicular directions. So no matter in which direction we orient the crystal, we will always have a kind of 2-dimensional grid. We will have some pattern, more or less like this, maybe more or less complex. And the same as I told for the C waves, we can go back and reconstruct the crystal itself. This is how X-ray diffraction works in case of single crystal diffraction. So we irradiate the crystal by X-rays, we create the same kind of pattern with some bright spots where the beam passes, and after that we can go back using Fourier transformation of this picture, and we get the distribution of electronic density in space, and from this distribution of electronic density we can reconstruct the molecule, the arrangement of ions in some inorganic material and so on. So for single crystal, in fact, today it is not so complex task, and I would say that if you have a molecule not bigger than a few tens of atoms, it is very straightforward. The biggest problem will be to grow the crystal. So if you have the crystal, you can collect the picture and you can more or less quickly reconstruct it to the structure of this crystal. But what happens if you cannot have the crystal? This is where the powder diffraction appears. So it can happen either if you really cannot prepare the crystal. For example, for high temperature superconducting materials, normally they cannot be grown as big enough crystals. You can only have them in form of powders. Or you want to work with some real material, like material in real operation conditions, or you want to investigate some solid mixture, like, for example, cement, which is never a single chemical compound. It is a mixture of different compounds. Of course, in this case, you cannot have a single crystal of this. So we go here to powder diffraction. The idea of powder diffraction is that instead of one big crystal, we make a set of big amount of small crystal. Typical size of the crystal for powder diffraction is about 1 micrometer, more or less. It can be like several hundreds of nanometers, or it can be few micrometers, but not bigger normally. So this gives us essentially millions of such small crystals inside the area irradiated by X-ray beam. And with this, instead of a set of separate spots, we have the rings. So if we put the beam, we put this powder sample on the way of the beam, the beam is diffracted more or less like this, with more or less uniform distribution. In the ideal case of ideal powder, it will be completely uniform distribution of the intensity around such ring. So the only parameter will be the angle between the incoming beam and diffracted beam, which we normally denote as 2 theta. So, and we can analyze this diffraction pattern using either point detectors, which we just scan along these 2 theta angles, or we can take one-dimensional detector, which gives the picture across some angular range, or we can use even 2-dimensional detector and get the whole diffracted rings. And after collecting this picture, we essentially get what we call diffraction pattern, which is intensity versus 2 theta angle. This is how it looks in real life. So on top, you can see the data collected by 2-dimensional detector, and in the bottom, it is like normal diffraction pattern by 1-dimensional detector. In fact, I think this is. So what do we do with this? In fact, we can extract lots of different data from this diffraction pattern. We can perform phase analysis. This means that we can find out which phases exist in the mixture and how much of each phase we have. We can still perform structural analysis. We can determine the structure. It is much more complex task compared to single crystal diffraction, but it is still possible. Of course, if we can combine this experiment with some external conditions, we can investigate stability of the materials, possible phase transition inside these materials, including chemical reactions and so on. Also, coming to practical cases of the material in its real operation condition, we can analyze its microstructure, most importantly, size of the crystallites when they are really small, below, let's say, 100, sometimes 200 nanometers. We can try to calculate the size. And we can investigate microstrains, so difference in lattice parameters across the sample, which is also quite useful in some cases. And we can perform experiment on microdiffraction, analyzing a very tiny part of the material and doing the mapping, which is, for example, widely used in cultural heritage experiments where people investigate how different parts of some historical object was created, how they work, and so on. All this information we essentially extract from three main parameters. Positions of the peaks that are determined by the periodicity of the crystalline structure using this famous Bragg law. Intensity of the peaks, they are determined by the types of atoms that exist inside the material and their positions inside the unit cell. And where is it? And the width of the peaks normally corresponds to all these microstructural features such as strains, size, maybe stacking folds. So basically, unlike what Alejandro just said for X-ray absorption spectroscopy, which can be only done in synchrotrons, powder diffraction experiments can be done using just laboratory X-ray sources. So why do we want to do this at synchrotrons? So what's the difference? Compared to laboratory sources, main characteristics of synchrotron sources are its very high intensity, high monochromaticity, so we have very narrow distribution of energy of photons, and also still we can change the energy of the photons, the wavelengths of X-rays, depending on what we want to analyze. And with using these three main characteristics of X-ray beams, we come to big advantages of synchrotron X-ray powder diffraction compared to laboratory experiment. First of all, we have very high signal-to-noise ratio. We have high angular resolution, so we can resolve very close peaks. And we can collect the data at very high speed, down to microseconds. It means that we can really follow some transformations in real time, which is also very useful and normally cannot be achieved using laboratory devices, even though the modern ones are already quite fast, but still not as fast as synchrotrons, of course. So how it works in case of our beamline, MSPD. So this is the technical drawing of what we really have. We use superconducting Wiggler as the X-ray source. Then X-ray beams passes through the mirror, and with this mirror, we either collimate the beam into a parallel one or focus it on the sample, depending on the kind of experiment that we want. Then we have a monochromator that selects the wavelengths that we want to use. And after that, the beam comes to experimental hatch, where we have two experimental stations. One we called powder diffraction station, which is like more similar to classical laboratory experiment. We will see it later today. And the second one, high pressure micro diffraction station, where we additionally focus the beam down to more or less 20 micron size, and we can perform micro diffraction experiment, including high pressure experiment using the diamond element cells. So this is how it looks like. On the left, you can see, and you will see it much better today, the powder diffraction station with two detectors, the point detector MAT and linear detector methane. And on the right, this is how it works for high pressure stations. Here you can see the typical diamond anvil cell where you perform the experiments under high pressure, and two-dimensional detector ionics, as you have seen before. So here we collect the whole diffraction ring. Just to compare with with laboratory techniques, you can see that this is the same sample that was measured in usual diffractometer and at our beamline, and you can immediately see the difference. So this is what the quality of the data that we can get here in essentially in 1 minute, and this is what was collected more or less in 1 hour in the laboratory device. So of course the improvement. And on the right is what happens if we want to perform high-resolution diffraction experiments. So both diffraction patterns were collected at our beamline. The bottom one is with linear detector, which is high speed, but a bit lower in angular resolution. And on top, it is high resolution. So we sacrifice a little bit the signal-to-noise ratio, but we gain in angular resolution. For example, here it looks like it was 1 peak, but in reality it is 2. We clearly separate them here. Of course, all this cannot be done without corresponding sepal environments. So we have plenty of them. We have also the cryostat for liquid helium temperature. We have cryostream device that can be used down to liquid nitrogen. We have hot air blower to high temperature, almost to 1,000 degrees centigrade. We have setup for electrochemical experiment. In fact, several setups depending on the type of experiment, type of cells. And we have the gas cell that allows us to work under controlled atmosphere. And for high pressure station, of course, we have the diamond annular cells themselves, and they can be combined also with different temperature control systems. So from industrial point of view, which kind of research can benefit from our beamline? Of course, it is batteries. We always have both real industrial experiments and experiments of applying science, but from academic institutions. And from academic institutions, batteries probably are used the most of time at our beamline. From industry, of course, we also have battery experiments, maybe not so many. We can work with cements. Also, it is quite active community that benefits a lot from powder diffraction. Pharmacy, pharmaceutical compounds. This is our main industrial clients. So we really have lots of experiment in investigation of solid forms of pharmaceuticals. We can investigate solid-gas interactions, as I've shown with this cell. It can be, for example, gas storage like methane storage, hydrogen storage, CO2 sequestration for ecological tasks, and so on. And of course, we work with catalysts. The catalytic reaction itself, it does not change that much. We expect that catalysts should not change during catalytic reaction, so we should not see much difference. But for modern catalysts, there is also an activation process. And this activation process of the catalyst, it includes chemical change, and we can see these changes. For example, here, mixed platinum-palladium catalyst was investigated, and it appears that during its activation, it first oxidizes to corresponding oxides and then reduces back to the metals. And only after that, the catalyst starts working. Okay, so this is basically all that I wanted to show you. Just to summarize, so X-ray powder diffraction for material science is probably the core technique. Everything starts with powder diffraction, most typically with laboratory, and then if you need more detailed information, you go to synchrotron. Because at synchrotron, you have better results and get them in shorter time, and this shorter time gives you access to in situ and operandi studies. And for more complex cases, like big unit cells, like pharmaceuticals, zero lights, metal organic frameworks, you need high angular resolution, and this also can be only achieved by synchrotrons. Well, so this is all. Thank you for attention, and I don't know if we have a few minutes for questions.
Alexander, any question for Alexander? Fraction?
Yeah.
Yes. Just wait for the question to be recorded. Okay. Thank you.
Thank you very much. If you are performing phase analysis, do you need to have some reference spectra, or you are doing it completely from scratch?
Well, normally it is done using the databases. Today there are really big databases that can be accessed, and you can search. In most cases, it is enough. I will show you how it works during the practical session. We will really do this. We will try to search we'll try to do phase analysis using the database.
Okay, and I have a fast second question. You have this superconducting wiggler manufactured in-house or by some third party
It is
company?
third party. It is Budker Institute in Novosibirsk in Russia.
Okay, thank you very much.
Any other question? If I may have a question related with industry again, I mean, the same question. I mean, you have normally industry requires high throughput. You have a sample environment or sample for doing high throughput measurements, and also how to treat all this amount of data that sometimes is coming from. Okay.
Okay. So at the moment, we are not really at the point to do really high throughput, like hundreds of samples or so. So at the moment, we have 4-position sample changer for usual diffraction experiment, and we have 8-position changer for battery experiment. Of course, yes, at some point, probably we will have to go to really high throughput and create some changer for many samples. I know that it was presented in the last European Powder Diffraction Conference this June by SRF. They constructed a really nice device where they will have, they will be able to measure hundreds of samples and less than 1 second per sample, so it will be really high throughput. In our case, we usually get lots of data when we do in situ or operando studies. It can be like heating of the material, cooling of the material, electrochemical reaction where the structure changes. This is where we really have hundreds of patterns normally. And to analyze this, modern X-ray analysis software has this option of so-called sequential refinement. So you start with really refining your starting structure or composition of your starting mixture. And then, because each next pattern differs only very little from the previous one, it can be automatically adjusted. And so using this, you immediately, in a few minutes, you have refinement results of hundreds of patterns. This exists at the moment, and we can use it.